A bird is flying at a constant velocity of 10 meters per second at an angle 20 degrees below the horizontal. At some point, the bird mistakenly flies into a 3-meter high window because it cannot see the glass. It bounces off the window in the opposite direction with a horizontal velocity of 4 meters per second. If an observer on the other side of the window first saw the bird when it was 16 meters away from the window horizontally, how much time has passed between then and when the observer heard the bird hit the ground? How far away did the bird hit the ground? And when the bird hit the ground, what was its vertical velocity? So we're going to start this problem by drawing a triangle here so we can find the horizontal component of the total velocity. This is 20 degrees below the horizontal. So what we're going to do is put the horizontal component as x and the total as 10 meters per second going that way. So what we're going to do is use cosine of 20 degrees equals x over 10 meters per second. And that way we can find x, which will be the horizontal component of the velocity. By putting this equation into the calculator, we find that the horizontal component of the velocity is 9.40 meters per second squared. Now, using the equation, displacement equals the initial velocity times time plus 1/2 times the acceleration times time squared. We can then cross out 1/2 times acceleration times time squared because acceleration equals 0 meters per second squared because it's horizontal. Now, we can also put in that the initial velocity is 9.40 meters per second, which we found above because we're finding the horizontal displacement. According to the problem, the horizontal displacement is 16 meters because that's how far away the bird was when the observer first saw it. Now, if we plug this all into the equation, we get 16 meters equals 9.40 meters per second times t. Now, we divide out 9.40 meters per second so that we have t on one side, and now we can perform unit analysis. So now we can cancel out 2 meters and then let this equal 16 over 9.4 seconds. And according to the calculator, this turns out to be 1.70 seconds. Now moving on to the next part. Horizontally, we know that there's no acceleration because there's no gravity horizontally. And because the problem said that it bounced off at 4 meters per second horizontally, we know that both the initial velocity and the final velocity for the horizontal component is 4 meters per second. And then the vertical component, because of gravity, the acceleration is minus 9.8 meters per second squared. And the initial velocity is 0 meters per second. And because we know the window is 3 meters high from the problem, the displacement is negative 3 meters. And everything else right now is an unknown. Now that we know that the initial vertical velocity is 0 meters per second, we can use the equation displacement equals the initial velocity times time plus 1/2 times the acceleration times time squared and get rid of the initial velocity times time because the initial velocity is 0. Now plugging that all in, we get negative 3 meters equals 1/2 times negative 9.8 meters per second squared times time squared. Now if we divide everything out from the right hand side except for time squared, we can now perform unit analysis because we have time squared on one side of the equation and everything else on the other side. Now that we have our unit analysis set up, we can cancel out the meters and we get negative 6 over negative 9.8 seconds squared. If we put that into the calculator, we end up with 0.61 seconds squared. This is our value for time squared. And if we take the square root of both sides, we get the square root of time squared, which is simply time, equals the square root of 0.61 seconds squared, which, if you put it into the calculator, ends up being 0.78 seconds. And this is our value for time for both horizontal and vertical components because time does not differ between them. Now, if we take the 1.70 seconds we got earlier in the problem for the time that it took for the bird to get to the window in the first place and add that to the 0.78 seconds that we just got, we end up with 2.48 seconds. And this is the total value for the time between when the observer first saw the bird and when the bird hit the ground. Now that we have our time, we can use the equation acceleration equals final velocity minus initial velocity over time for the vertical component and plug in the known values, which is everything in this equation except for the final velocity. Now we can multiply both sides by 0.78 seconds in order to get final velocity on its own because the initial velocity is 0, so we can just cross it out. So now we can perform unit analysis. After we cancel out the seconds, ends up getting us negative 7.64 meters per second for our final velocity vertically. And this is our answer for how fast the bird was moving vertically when it hit the ground. Now we can use the equation displacement equals initial velocity times time plus 1/2 times acceleration times time squared for the horizontal components. We can get rid of the 1/2 times acceleration times time squared because the horizontal acceleration is always 0. Now, if we plug in the known values, which is everything except the displacement, we end up with 4 meters per second times 0.78 seconds, which means we can now perform unit analysis. Now, after we cancel out the seconds, we get a final answer of 3.12 meters for the horizontal component of the displacement. This is our final answer for how far away the bird landed after it bounced off the window. Now, for the final answers to this problem, we end up with the time between the observer seeing the bird for the first time and the bird hitting the ground at 2.48 seconds. The bird landed 3.12 meters away after bouncing off the window, and as the bird landed, its final vertical velocity was minus 7.64 meters per second.